A fair amount with FreeBSD embedding, so I'm going to talk about the ways to embed things and also try to run through an example using FreeBSD to create a console terminal server. So I'll talk a little bit about why to use FreeBSD in an embedded environment today, talk about what is embedding and what situations would work well for FreeBSD, and at the end I'll talk about some of the things that FreeBSD needs that would help improve the embedding experience for the people doing the embedding. Okay, why FreeBSD? One of the biggest reasons people use FreeBSD instead of other alternatives out there is license. It's a completely free license. You don't have to worry about intellectual property issues like you would with some other licenses. You don't have to pay for it like you would with some other licenses. A lot of people will try to use GPL-based systems, but then try to do an end run around the GPL, and by having drivers that are split into user space and kernel, or other methods to try to avoid leaking in GPL contaminated code. Well, you can do that. FreeBSD is an easier solution because you can just pull the stuff you need to into the kernel, pull the stuff you need to in user land, it all just works. And as most people here know, FreeBSD has a fairly proven track record. A lot of companies are using FreeBSD presently to embed, creating products embedded with FreeBSD, Ironport, Julian, Nokia, a number of other examples. Cisco even is using FreeBSD in a few limited areas right now. So what do we mean when we're talking about embedding computing? The term has a lot of different meanings depending on the segment of the market that you're looking at. So I'll talk a little bit about some of those and where FreeBSD fits in well and where FreeBSD doesn't fit in maybe so well. So in the traditional embedding environment, we have a very tiny runtime executive. It tends to be a proprietary executive. It tends to be real-time or pseudo-real-time. These environments tend to be very tuned for a particular application. It's very difficult to take your application from one environment to another, run new applications on your environment. For the environments that they're in, they work extremely well. You can go up to an ATM machine, punch in your PIN, and you get cash. And the bad guys usually will get access to your account. But these solutions tend to be very proprietary and very expensive. And FreeBSD doesn't fit really well with the traditional embedding. Its kernel is much larger than this. So, in the less traditional, more modern embedding, a number of things have changed. In the early systems, you had kilobytes to worry about. Now you have megabytes, multiple megabytes to worry about or to play with. This fits FreeBSD's memory footprint better. Most of the systems that you would embed into have an MMU, which is important for running most Linuxes, or most Unixes, Linux, BSD, even Windows can take advantage of an MMU when it's there. The applications that have operating systems embedded in them are become progressively more and more sophisticated over time. You have systems that do firewalling and mail filtering. You have applications that are complete DVR that interact with the user in fairly sophisticated ways. There's a number of different chip manufacturers competing in this market space. So you've got processors that have ARM, Intel, MIPS, PowerPC, and a few others competing in this market space from vendors that are very, very diverse, multiple vendors for each one of these architectures. In addition, in the embedded space that perhaps distinguishes it from the more traditional desktop or server space. You have more diverse bus topologies, you have more diverse interconnection between the processor and the bus. There's a lot of very specialized serial buses that speak different protocols to the different devices that you don't typically run into in a server environment. Flash is a bigger part of the picture, and oftentimes you need to worry about tuning. The tuning parameters in an embedded environment is going to be different than in a traditional server environment. So up here I've listed a number of the continuum that you see FreeBSD embedded into, or that you see in the embedded environment. At the top end, I put a rack mount server that might have several disks, a RAID array, multiple NICs to do routing. Just below that would be the x86-based appliance, where you've got a processor, a couple of cards, maybe a wireless access point, a console server, that kind of thing. And then down on the power scale would be some sort of multi-core embedded processor. This would be the PowerPC like 8572s that Motorola produces, or there's several different vendors that produce these. Cavium Networks has an Octeon processor which scales from 1 core up to 16. The next level down would be just a single core microprocessor. What distinguishes the microprocessor from the microcontroller: the microprocessor tends to have more parallel buses. The microcontroller tends to have more serial buses, fewer pins. The pins tend to be more multiplexed. Since they multiplex the pins and have fewer pins, typically they consume less power. Then below that, you've got CPUs that eliminate the NMU entirely, so that they consume even less power. And then small PIC controllers that people use in extremely embedded environments. The last two are not really well suited for FreeBSD. They tend not to have enough memory, not to have enough horsepower to run FreeBSD, so I won't talk about them in the rest of the talk. FreeBSD's target market. One of the areas that FreeBSD works well, where are the areas that if you want to embed FreeBSD into your product, that you will have a good success. I'll talk about some of the problem domains where people have embedded FreeBSD. I'll talk about some of the architectural support, which is more important in the embedded space. And for servers, everything's Intel, so FreeBSD runs on Intel, so you don't have to worry about that. For the embedded space, you need to worry about it a little bit more. Plus, I'll run through some of the packaging solutions that FreeBSD has that lets you deploy into an embedded environment. So the areas that FreeBSD works well in. FreeBSD has a very good wireless stack, thanks to Sam Lethworth. There are a number of companies that are using FreeBSD for their wireless access points or have embedded FreeBSD's wireless 802.11 stack into their operating system. A number of control systems are running FreeBSD. These are things that measure flows in pipes. The examples that my past employment was, we used FreeBSD to control, measure atomic clocks, figure out which atomic clock was running a little fast or a little slow, recover UTC from GPS, satellites. There were a couple of applications we did that had military overtones where we were controlling transmission with the FreeBSD system, transmissions of signals to be precisely on time. Another area that FreeBSD has done very well in is network servers and routers. There's at least one major router company, Juniper, that uses FreeBSD, or they use a variation of FreeBSD called Junos in all their routers. There's a company called Ironport, which my employer recently purchased, that has a number of network server-based appliances for filtering email and network traffic and web traffic. A number of the large DNS and web servers on the net are run on FreeBSD. A lot of people have made products. X Systems is one that sells products into this area. And another area that people have done well in embedding FreeBSD are for NAS devices. These are the network attached storage devices. FreeNAS is one of the players in this area that allows you to convert a PC into a network attached appliance. So if you're looking to, if your application is in one of these domains, problem domains, chances are very good you won't be blazing a trail. FreeBSD has already been there. The architectures that FreeBSD supports that are important to embedded computing, I've mentioned them already. I'll just let people read this for a second. So there's a number of different packaging solutions if you want to deploy a system based on FreeBSD that you can use. The first one is the venerable sysinstall. The advantage is millions and millions of people have run it. The disadvantage is that it's well understood. I mean, the advantage is that it's well understood. Its limitations are also well understood. It's good for installing onto systems, primarily desktop, where you have a need one of the standard subsets that FreeBSD packaging system provides. FreeBSD's subsetting is fairly coarse, fairly coarse-grained, and you need a lot of disk space, relatively speaking, to install FreeBSD using sysinstall. One of the biggest limitations of using sysinstall, however, in the embedded environment is that it is not well suited for scripting. Typically, when you're building a system, you want to put your applications on the system, you want to have that be scripted somehow so that you get a reproducible result each time. Sysinstall can be made to do that. And I see some people wincing in pain, knowing just what pain is involved with doing that, but it's not well suited for that. It's certainly not something you can let novice users doing or people new to the experience to do. A few years ago, and partially in response to this, Paul Henning wrote NanoBSD. So this is, or NanoBSD. This is a set of scripts that allow you to more finely tune the subsetting of FreeBSD that you do. It allows you to subset in the build as well as in the deployments. And this is important because you want to build all the compilers when you're building a system, but you don't necessarily want to put them onto the actual system. As one example, there are, you want to potentially build all the documentation tools, but you don't necessarily want to put the documentation tools in the man pages on the final product. This slims down FreeBSD tremendously. You can easily build a NanoBSD system in the 20 to 30 megabyte range. It supports field upgradability through ping-ponging. A lot of the compact flash parts that this is targeted to have gotten much larger than this. So it's very easy to deploy NanoBSD-based systems. My router at home is a NanoBSD-based router running on a Socris box, for example. It also works well when you've got an SD card system, if you've got a system that can boot off SD cards. Where it doesn't work so well is there's really not a lot of support in NanoBSD for creating images that would work well in a NOR or a NAND flash-based system. You can't take a custom bootloader and put it at the beginning, can't create the partition tables necessary for that. Excuse me. And the other problem with NanoBSD is there's no cross-compilation support. Cross-compilation support is fairly limited. I know that there's efforts underway to fix this right now, but that's one disadvantage if you're trying to deploy to ARM or to PowerPC. You need to have an ARM or a PowerPC server to build everything. Another option you have with FreeBSD is TinyBSD. NanoBSD is an opt-out system, where you say, no, I don't want a compiler, no, I don't want SendMail, no, I don't want LPR, LPD. You have this big list of no, 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 I don't want this, I want this. TinyBSD takes the other approach. It says, I want LS, I want RCP, I want SCP, et cetera, et cetera. You give it a list of things to include. It does some dependency checking based on the modules that you give it so that all the shared libraries are pulled in correctly. It does some housekeeping to make sure that some of the other scripts and config files that you need to boot a system, like etcfs tab, are built correctly. You have a password file. It creates a nice image. You're able to shrink FreeBSD down to between 15 and 20 megabytes using TinyBSD fairly easily. Again, one of the disadvantages of this, it's also the advantage, is that you have to have a profile that lists everything that you want, and this can be difficult to create the first time. Julian.
Though you say it up there, it's worth pointing out that it uses the system you're building on to source all the files. So
right.
You don't compile anything. You can build a system in 3 minutes, find it's wrong, and build another one.
Right. That's one of the points I was going to get to. Although TinyBSD does support cross-compilation to a limited extent, typically it'll just pull the files from the system you're using so that you can build it without building the system. It's a binary. It's more of a binary-based system. And the way the cross-building works is it cross-builds the system and then pulls the files out of there, or it pulls them out of that cross-built system. So I say it has limited support for cross-compilation. You can give it basically a tester to go look at when building like an ARM system. But you can pull a TinyBSD system together very, very quickly. It's very, very fast. If you're deploying a system that where the host and the target are exactly the same. One of the other options that's in FreeBSD is PicoBSD. It's not very well supported right now. The scripts barely work. One of the big advantages, though, is its size. You can create a 4 to 8 megabyte file system with PicoBSD. The technology that PicoBSD was based on is called CrunchGen, and that basically takes all the files and the libraries and crunches them together into one binary. That technology works really well, still well supported. In fact, FreeBSD/rescue directory is built using that technology. And I've done some experiments with other packaging of the /rescue directory, and I've gotten on an ARM system a 3 megabyte root file system, including the kernel. So it allows you to produce a very, very small system. The big disadvantage here, though, is that TinyBSD was a little bit of a pain because you have to list everything. This is an even bigger pain because you have to list everything and get all the dependencies right. And if it all works, it's great. But if it doesn't all work, it can be difficult to debug. In the end, the results are usually worth it for people that need to have very, very small footprints. Again, there's no NOR or NAND imaging support in this. Okay. So those are the different packaging technologies that FreeBSD has. Before I get into the example, the one other one that people tend to use is they tend to roll their own. They tend to create their own set of packaging environment so that they can get the best of each of these worlds. Some of these packaging systems were created before TinyBSD or NanoBSD existed. Some of them were created in reaction to them. So the example I'm going to give today is a console server. I have a lot of embedded boards at home. I've needed to log into their consoles. They're all serial port based. Some of them are normal RS-232 level drivers. Some of them have 3.3 volt level drivers. It'd be nice to be able to support all of them with one box. It would also be nice if this box didn't consume a whole lot of power. I've got a lot of boards. I'm using enough power as it is. And it would be good for the box to control the power of the digital board, so I can turn them on and off remotely while I'm sitting in my office. I don't have to go out to my garage to do this. So I created a prototype system. And this is kind of the normal way that you would create an embedded system. Create a prototype system that was very easy to do. I used one of the older Socrates net cards, plugged a USB card bus card into it, plugged a hub, plugged USB serial adapters into that. I had my prototype. I was able to use MeetBSD to create a compact flash image that I would boot. It was fairly easy to pull all this together, but the individual components of the hardware that I needed to do this were about $500 off the shelf, so it was kind of expensive, and it used about 20 watts of power. So I have a couple of pictures. I didn't actually take a picture of the finished system, so I'm mocking this up a little bit. But as you can see here, we've got this is the basic board that you get. So I added a compact flash card, added a USB card bus card, plugged a USB hub, and used a combination of PLCOM and FTDI parts to populate that. The FTDI parts actually support 3.3 volt direct wave that I have. The PLCOM are for RS-232. And this worked fairly well. I could telnet into this box. I was running software on the box that would capture all the output from the console, even when I wasn't connected. Running con server for people that are familiar with it. It would log everything. It was a fairly nice little box. But there's really a lot of redundancy in this design. If I was to produce this for real, as a shipping product, there's some problems there. First of all, I don't need the hot pluggability of the card bus slots. That's a waste. It has 2 NICs. This application only needs 1 Ethernet NIC. I don't need this to be a router also. I didn't use the mini PCI slot either. This is completely wasted. And the compact flash cards have like 50 pins, and that's a lot of expense to worry about when you're routing boards. Same thing with the mini PCI. All these pins go to the mini PCI that wasn't used, so it's doubly expensive. Not only are there a lot of pins, it's completely unused. So, those are some of the disadvantages of going with this design. It was easy to prototype, easy to get the software running. Now I want to move to a lower cost solution. So in investigating the different solutions out there, I came upon the Atmel part that's listed up here. It's kind of a mouthful to say. And this gives you a block diagram of the basic system. So this is kind of the cost reduction phase. Atelier makes a system on module part. System on module is basically a system on chip with all the glue logic, flash, RAM, maybe transformers, 5 parts, that kind of thing. An SoC is a system on chip, which is a CPU and a bunch of peripherals. So I found this system on module. That was a fairly complete system. It was less expensive than the Socrates board, also much smaller. The Socrates board is about this big, and these system on module boards are about this big. And the system on module not only brings out all the USB and Ethernet, it also brings out all the serial ports that this chip has. There's like 5 different serial ports that are supported with this chip. It brings out all the GPIO lines and so forth. One of the things that Atelier also sells, I'm not up here trying to sell you on them, there's 4 or 5 different vendors you could use, is they have a carrier board that you can plug the system on module into. And it brings out an SD card, the 5 serial ports, GPIO, etc., which I've kind of labeled here. For people that might be interested. And this was a fairly effective way for me to do development. I had the system on module that I was going to use in my final system. If I was ever to build it as a commercial product, I had all this stuff brought out. I could very easily prototype as well. So The areas that you save money moving to the ARM. The ARM is a cheaper processor. The AMD processor is about $15 in bulk. This ARM processor is about $5. At least when I was doing the comparisons, these numbers may have changed. You move from having 50 pins of compact flash headers down to having 8 pins for the SD card. I was able to get direct support for the 3.3 volt serial devices I wanted. So I could completely eliminate USB as a requirement. That was there for expandability if I ever needed more ports. But with 4 available serial ports, I was able to connect most of my boards most of the time without even needing to have USB. So that also produced a power savings as well. And it's also a much smaller footprint. Some of the things that I plan on doing with this design in the future. Although SD cards are nice and inexpensive, this part has built-in NOR memory. It would be better just to move everything into the NOR memory. There's plenty of it available on the card. This eliminates another part. I'd like to be able to do power control via GPIO lines. I never got around to doing that part of the project. I also have little LEDs, status, and temperature sensing and those kinds of things. Also, if I was going to make an actual product out of this, I would move to a custom board with the Atmel part, the memory, the flash, and just the pieces I needed on that board. So again, further reduce costs, particularly if I was going to have a high volume system. So on this unreadable slide are a number of URLs for the different things I've talked about today. So what have I learned from this project? Well, I've learned that FreeBSD still needs a number of areas, a number of improvements in the base system to make this easy to do. We need to have better flash support. Juniper Networks recently donated a driver for CFE-based parts and Intel More-based memory. That's been helpful, but more bridge drivers need to be written for it so that we can put it on more boards. We also need to have better flash file systems. UFS is okay, but it's just okay. It's not great. It's not a great file system to have on flash. There's no wear averaging. There's no wear leveling support in UFS or in anything in FreeBSD. There's not a generic flash layer like you have in Linux, the MTE devices. So there's a lot of shortcomings currently in FreeBSD's flash support. In addition, we need better imaging tools. We don't have any tools right now that will produce an entire image for to put into flash. We just don't have them right now. We don't have the bootloader support. We don't have the tools necessary to pull all the pieces together to create the partition tables. We don't have the geom modules that understand these partition tables and can present them to the user when the system boots up. It's very difficult to produce an image. There's a lot of manual tinker. It's difficult for someone just to try this out. One of the other things that I learned during this, this project was that etc rc.d boots very, very slowly. On my Atmel board running off an SD card, I can boot the kernel to the mount loop prompt in 2 seconds. Loads the kernel, decompresses it, goes all the way through all its probes, 2 seconds. From the beginning of rc.d running, when I started, to log in, took 5 minutes, which really is a rather significant customization. Getting rid of the low-hanging fruit on the startup, I was able to optimize that to 2 minutes. But there's a lot of optimization that could happen. Alternatively, we may want to investigate having a reduced functionality etcrc script that would be good for an embedded system, would be good for a system that has limited memory, where forking is more expensive than on servers, and that kind of thing. And that would be a useful project for people to work on. One of the other things that would be useful in the embedded space for FreeBSD is more SoC support. I was fairly limited and constrained when I was looking for different CPUs and architectures to run FreeBSD on, because the base level support for those is still limited and mature. So these are all areas where we need to improve. And that's my talk for today. Philip Paeps gave an earlier version of this talk at EuroBSDCon and helped with the production of it. You can find my slides at this URL. I'll also be mailing them to Randy so that they will appear on the site. So does anybody have any questions at this time? Yes?
So rumor has it you also do MIPS work, correct?
Yes.
Just a little bit?
Just a little bit.
I'm wondering what the status of embedding FreeBSD on more consumer networking boards, like the Linksys of the world.
Okay. Right now there are 2 or 3 different projects trying to get FreeBSD up and running on the different Linksys boards. They primarily use Broadcom chipsets. Those boards, and that we've got a kernel up and running, but we're hampered by not having the imaging and packaging tools that something like OpenWRT has. It's harder to pull all the pieces together. The ports collection right now doesn't cross-build, so it's hard to bring in packages. Some of them do. You can kind of make it work, but it's still kind of hokey. So we're still a little ways away from being able to deploy to those systems. We do have a couple of images available for the ADM 5120 class boards. If you've got enough flash on one of your evaluation boards, you can do that. Not too many wireless products are based on that. Some of the printer and gateway products are based on that. So there's work in that area. That's an area we would love to see more people involved in. Now that we've got the basic kernel support going, we're not there today. Yes?
What are the minimum requirements on the ARM platform these days?
The minimum requirements on the ARM platform. That's a good question. I've run on the ARM platform in 16 megabytes of RAM with off of an image that was 12 megabytes. I've also run off of an image that was on a 32 megabyte system off of a CrunchGen image that was 4 megabytes, but that really didn't have enough. That just had the basic networking tools. It didn't have enough really for a full system. So you're looking at numbers, 8 megabytes or more of RAM, 4 megabytes or more of flash. More realistically, 8 megabytes of flash and 16 or 32 megabytes of memory would be good, kind of low-end numbers on the ARM to look at. I know people that are deploying systems today that have a very large SD card with 32 megabytes of RAM for controlling GPS time recovery for digital broadcasting networks, for example. Yes?
What is it about the RC scripts that is so slow? Is it the work they're doing, or all the shelling and file I/O?
Mostly the shelling and file I/O. The file I/O is one small component, but the bigger component is all the execs that are in the shell scripts. One of the low-hanging fruit optimizations that I did was to eliminate an exec to pull in shell variables. And one exec, and the other optimization I did is I deleted all the scripts I didn't need for my platform. Those were the 2 main optimizations I did. That reduced the amount of I/O, that reduced the amount of forking significantly, and that's where I got most of my gains. So that's the primary reason, at least on some of the embedded platforms, where you've got slow I/O and a costly fork exec environment.
I'll ask another one.
Okay.
Do you have a feeling for what the future of software-based flashware leveling is going to be? I mean, I kind of get the sense that the devices themselves are going to start handling that more, and maybe software algorithms are going to be less important.
That's certainly been the trend over the past several years. If you go back and look at old 4 and 8 and 16 megabyte compact flash cards, for example, they have almost no wear leveling in them. If you go out and buy a compact flash card today that's however many gigabytes it is, 4 or 8, you'll find that it has very sophisticated wear leveling algorithms in it. The same is less true for the raw flash controller cards. They seem to have very little wear leveling built into them today compared to, very little more compared today compared to what they were like 5 or 10 years ago. They still expect software to do all of the wear leveling. Now, there are some parts you can buy that look like IDE drives that have wear leveling built into them. So that you can put it onto a local bus in your embedded system and get the wear leveling. But typically, the technology there hasn't kept up, again, because they're a more price-sensitive item than the compact flash cards even that you buy, which should tell you something. If the compact flash cards you buy are like dirt cheap, 10, 20 bucks. The embedded controllers for the flash parts on the embedded systems, if you can shave a nickel off of them, people love you, and nobody buys the other ones. So in the future, there might be more and more wear-level parts, but right now there's still a need to do that in software. Any other questions?
Someone asked me at MeetBSD if anyone's working on executing place on UFS.
Okay, so the question was, is anybody working on an execute in place on UFS? And I'm not aware of anybody that's doing that. I assume for a memory mapped flash system that can execute out of the RAM or out of the flash rather than copying it to RAM like it's done today. I don't know of anybody that's working on that. If somebody is, I would be very interested in hearing from them, but I'm not aware of that. The closest thing that we have to that today, though, is the boot sequence for ARM and soon MIPS will run directly out of the flash. So you can store the compressed kernel in flash. We jump directly to it. The bootloader supports that. Execute in the flash, decompressing to memory. And that works out fairly well. Yes?
You said the Socrates box was about 500, so what did the ARM box cost?
The ARM box costed about 300 with all the evaluation software, the evaluation board, the system on chip module, the USB hub, the SD card, and the different dongles you attach to it. The actual board, you can get the actual board for closer to 200. The Socrates board, when I bought it new, was like 250 or 300. The additional cost for the Socrates was that there's also a card bus USB controller I had to add to the Socrates box that I didn't have to add to the ARM box. Anything else, or I guess we're done then. Thank you very much.